notes on 7-3, logarithmic functions as inverses. So we've been talking about functions and graphs and their inverses for a while, and now we're going to look at the inverse of an exponential function can be represented as a logarithmic function. Okay, the big deal understanding stuff is right here. So if we have the exponential function y equals bx is 1 to 1. That means for every x there's exactly one y. Okay, so its inverse is this, x equals b to the y. So that's a function also. Instead of writing x equals b to the y, we can write this as y equals log base b of x. Okay, which is what's written down here. Okay, and it's just a different way to write it. It's using logarithms as inverses. Okay, there's all sorts of information down here that we're going to talk about in class because the way it's written out in sentence is very confusing. Really, I think you'll have a better understanding of this if we look at some definitions and understand that we're using logarithms to write exponential equations in logarithmic form. Okay, so for example, what is the logarithmic form of each equation? So we have 100 equals 10 to the second. So if x equals b to the y, then log base b of x equals y. So all we're going to do is we're going to do some simple substitution. So if 100 equals 10 squared, then log base 10 of 100 equals 2. It's basically saying, like, what is the exponent for this base that will give us this answer? Okay, and the answer to that is 2. All right, that's what it's basically saying. So again, let's take a look here. We have 81 equals 3 to the 4th. Well, the question then becomes, what is the exponent that will take that base and get it equal to that value? So log base 3 of 81 is 4. Remember, finding the logarithmic it's the inverse of the exponential equation. So this is practice just with writing them. All right, so go ahead and pause the video here. See if you can get these rewritten. Okay, go ahead and pause the video now. All right, you've unpaused. Let's get some answers to these questions. Okay, so right here, it's really simple. We have log base 6 of 36 equals 2. For part B, we have log base 2/3 of 8/27 equals 3. And here we have log base 3 of 1 equals 0. And that's a 1, not an L. Okay, so we're just rewriting those. All right, we can use the exponential form to help evaluate logarithms. Okay, so we're going to go in the other direction sort of here to help evaluate them. So what is the value of log base 8/32? And what that's really saying is, and what happens right here is they transform this into an exponential equation. Okay, so we have 32 equals 8 to the x. Okay, because it's 8, that's the base, and then 32 is what it equals. So we have 8 equals 30. Sorry, down backwards. We have 32 equals 8 to the x. Now, what we have to do is we have to change the way this looks. Similar to a lot of equations that we solve, there is no exponent. 8 to the first is 8. 8 squared is 64. So the answer is somewhere between in between 1 and 2. We have to find where the answer is in between 1 and 2. We don't want to guess, but this does give us an idea of, if this were a multiple choice question, which it is, I can eliminate that, and that right away, and I know my answer is 5/3, but I want to actually understand why it's 5/3. So I'm going to change the way these are written. I noticed that 32 is 2 to the 5th, okay, and there's no way to do this. It's just something I noticed. I also know that 8 is 2 to the 3rd, and then that's being raised to the x, okay. 2 to the 3rd to the x is the same as power to a power we multiply, right? It's 2 to the 3x. Now what's nice is this is where we are right here. Once the bases are exactly the same, I can set the exponents equal to each other, which is exactly what I do. Since the bases are the same, the exponents must be equal. So 5 equals 3x, so x equals 3/5, and that's how we get b. Now, if it's not multiple choice, you would have to figure it out. It was multiple choice, so we were able to eliminate answers just based on this information right here. Go ahead and take a second. What is the value of each logarithm here for 2a, b, and c? Go ahead and pause the video and get values for each of those. Go ahead and pause the video now. All right, you've unpaused. Hopefully for 3a you got, or for 2a you got 3. Hopefully for b you got 5/2, and for c, toughie, you got -5/6. If you didn't, pause the video, try those again. Okay, try them again, see if you can follow the steps from this right here as far as how we did that. If you still can't, make sure you make note of it, and we'll go over it in class. A common logarithm, okay? A common logarithm is a logarithm with base 10. You can write common logarithm as log base 10 of x, simply as just writing log x. So when we have 10 as the base, we can just write log. We don't have to write this 10 down below. It's just assumed that it's log. You have to remember that mathematicians are insanely lazy, and if they can find a way to shorten their work, they're going to. Many measurements of physical phenomenon have such a wide range of values that the reported measures are logarithms, or exponents of the values, not the values themselves. When you see the logarithm of a quantity instead of the quantity, you're using a logarithmic scale. The Richter scale is a logarithmic scale. So, you know, we hear about the Richter scale anytime we hear about earthquakes or things like that. So this is a logarithmic scale. So in December 2004, an earthquake with magnitude of 9.3 on the Richter scale hit off the northwest coast of Sumatra. The diagram here shows the magnitude of an earthquake that hit Sumatra in March 2005. The formula right here compares the intensity levels of earthquakes, where I is the intensity level determined by a seismograph and M is the magnitude on a Richter scale. How many times more intense was the December earthquake than the March earthquake? Okay, so what we do is we're going to use this formula that they gave us. We're going to substitute 9.3 and 8.7 in, and then we get log, and this is I1 over I2 equals 0.6. So we know that that's log base 10. Okay, we apply the definition of the common logarithm. So we go from here to here, and the answer we get is 4. 10 to the 0.6 value, 10 to the 0.6 is 4. Okay, and that's simply because of the same stuff. We have log. If this is confusing you, this big variable, then I understand. We can walk through that. But this is log base 10 of I1 over I2 equals 0.6. And if you go back to earlier, when we had stuff like, for example, when we had the log of 5 is 125, we just did that one. We're basically saying 5 to, when we change that to exponential, 5 to the what power equals 125. Okay, well that's the same thing we're doing right here. Okay, except for here we have the equal sign. It's this number that's missing. Okay, this is that. So we rewrite this as 10 to the 0.6 would equal I1 over I2, and then you just put 10 to the 0.6 in your calculator. It's actually not that hard, and it lets us compare some things that maybe we wouldn't have otherwise been able to compare. In 1995, an earthquake in Mexico registered 8 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington State. How many times more intense was the 1995 earthquake than the 2001 earthquake? Use the same formula. See if you can do this on your own this time. Use the same formula and get an answer here. All right, you've undone it. Hopefully you got about 16 times. So only 1.2 more on the Richter scale, but 16 times more intense was the earthquake in Mexico. If you didn't get that, make sure you make note of it so we can check it in class, and I'll show you. A logarithmic function is the inverse of an exponential function. So where this is y equals 10x, okay, and remember, inverse functions can always be shown as a reflection in the line y equals x. So here's that line. So if you tilt your head, and many of you are doing that now, if you tilt your head, you can see that this function, you know, it's a mirror image across that line. So this down here in blue, yikes, this down here in blue is now our inverse, okay? y equals log of x. Okay, log base 10 of x. So 10, 1 is a point. All right. Recall that graphs of inverse functions are reflections of each other across that line y equals x. You can graph y equals log base b of x as the inverse of y equals b to the x. Okay, so for example, if we looked at graphing a logarithmic function, what is the graph of y equals log base 3 of x? Describe the domain and range and identify the y-intercept and the asymptote. So step one, it's probably just easiest to do step one first. So graph the exponential function, okay? And then the points you have, this is 0, 1, 2, 9, 3, 27, just switch them, okay? Just switch those points, and now there's our logarithmic function, okay? We just choose a few points and put them in. You can use a table of values, here for x and y, so 1, 2, and 3, and we get those, and then we just switch them for the logarithmic function. The domain for this logarithmic function is x is greater than 0. That was the range for the original function, so those switch. There is no y-intercept because that's the y-axis becomes the asymptote here. Y-axis and x equals 0 are the same thing. Okay? Let's take a look here. What is the graph of y equals log base 4 of x? Describe the domain, range, y-intercept, and asymptotes. And then take a look at part B, where you're going to suppose you use the following table to help you graph y equals log base 2 of x. Recall that if y equals log base 2 of x, then 2 to the y equals x. Copy and complete the table and explain your answers. Go ahead, pause the video here, see if you can get a graph for log base 4 of x, and see if you can answer part B also. Make sure you talk about domain, range, y-intercept, and asymptotes. Okay, make sure you do all that. Go ahead and pause the video now. All right, you've unpaused the graph. I'm just going to give you a quick sketch, guys. It's going to look something like this, and it comes up and turns and goes this direction. Yikes, that's ugly. But big picture things, the domain is going to be x is greater than 0. The range is all reals. The y-intercept, there is none. And the asymptotes here is x equals 0, or you could put the y-axis. And then if you want to know some values, you obviously can just put some values in. This is y equals, this is y equals 4 to the x. So if you made a table of values for the exponential and you put in 1 and you got 4 and 2 and then 16, it's going to get real big real fast, right? So you do those, and then we're just going to switch them for the exponential, okay? So if we did, this would be 1, 2, 3, 4. This would actually just be 1 if you're looking at your picture. Take a look at part B. If we were to complete this table, this right here is, this is undefined. This is undefined. This is 0, and this is 1. Okay, that completes the table. And then see if you can explain these answers. We're trying to figure out what could we put in here that would give us a negative. The answer to that is nothing. What could we put in here that would give us a negative? These first two, or that would give us 0, the answer is nothing. 2 to the blank equals 1, well that's 0, and 2 to the y equals 2, so then y would have to be 1. Okay? Let's take a look at families of logarithmic functions. So like anything else, we need to understand what the shift and compression and stretch and all that looks like. The function y equals log base b of x is the parent function. We can shift it, in similar ways, translating it like we have been the whole time with h and k. We can also use, you'll notice down here, a out in front of the log to stretch it. This stuff should really start to seem really repetitive at this point because we've done so many of these with how to shift a function. You take a look at this one right here, we should know right away it's going to be the base function, or the parent function, just shifted right 3 and up 4. It's not really complicated. It's going to change some things. Obviously, it's going to change the domain. It's going to change the x-intercept. It's going to change the asymptote, but it's not going to change the general shape. Go ahead and, for a second, if you could, how do these two graphs, how do they compare to the parent functions? All right, you've unpaused. Hopefully you got for A, this is 3 units right. It's 4 units up. Okay, the asymptote is now x equals 3. Let's see, what else do we have on this one? The domain is x is greater than 0. Okay, so that's the domain. For part B, it was stretched. Okay, stretched by 5. And then everything else, the asymptote, domain, and range are all the same. Okay, asymptote, domain, range, all the same. Okay, that's it for the notes, guys. This was some complicated stuff. Hopefully you come with questions, and I will see you in class when you have them. Bye.